So the company ScyllaDB is actually a spin-off of a company called Claudio Systems that were working on a microkernel. And it was when benchmarking applications for this microkernel that they noticed how slow Cassandra was. And they saw that there was a lot of potential in this space and decided to spin off the company to build this database. Cassandra is very widely adopted. There are a lot of companies using Cassandra, and we think that it has the right properties when it comes to scale. So it has the correct distributed systems, algorithms, right? That was the motivation behind choosing Cassandra. Cassandra has two main APIs, a legacy Thrift API and a modern one called CQL, which is a kind of query language similar to SQL. And it's a fully specified protocol, and we implement both of these interfaces. So you just use the plain Cassandra drivers to talk with Scylla. Okay, and everywhere that Cassandra is used, like as a backend for Spark, for example, you can just plug in Scylla. You just have to change the IP addresses to point to Scylla nodes. It's exactly a drop-in replacement. You just have to shut down the Cassandra service and start the Scylla service and benefit from everything. And also we're compatible at the file format level, so we're compatible with Cassandra 2.0 versions. But soon we'll be compatible with the 3.0 file format as well. The wire protocol between nodes is very different. We use our own RPC mechanism. So the company is about 35 people, have 20-something engineers. We see a couple of outside contributions to ScyllaDB. And we see a lot of contributions from outside people to the C-Star project, which underlies ScyllaDB. Actually, it's mostly systems programmers, people with virtualization experience of building. The founders built the KVM hypervisor, and a lot of people with kernel experience and low-level stuff. No, not really, because like the distributed aspects, they're essentially what Cassandra implements. Okay, so we don't do a lot of modifications to those algorithms, and when we do come up with our own stuff, it will be properly funded on. The I/O scheduler, the part that deals with disk I/O, has been in place for a long time, and that's something that is really necessary. So you have good latency for the user online requests, so we can properly put back pressure on the background processes and make sure they don't interfere with the latency of the really main requests. But most recently we've been noticing that we can do the same, for example, for the CPU, right? When we are scheduling all these continuations, some of them belong to user requests, others belong to background processes. And we were seeing some interference, right, where background processes were getting a lot of CPU. So we want to manage that as well. So our testing story is we have different levels of testing. We have, of course, unit tests. We have integration tests. And we also have JEPSON tests, for example. And we have tests where we built our own file system based on Fuse to inject failures on different system calls. See if we can handle those failures. We haven't really done anything with data corruption or anything, but eventually. But it's very well tested. A lot of the tests we also inherited from Cassandra, because the tests that deal with the system as a black box can work with Cassandra and with Scylla. So there was already a bunch of work done for us. So I've really enjoyed Kyle's talk on the JEPSON work, Christopher's talk also on Antidote.db. And today, Boaz's talk on Twitter storage, and also Teller's talk on